So, good morning and welcome to another Chai and Wine. Today being the first Sunday, we are live from a lab and we are live from the superconductivity lab of TIFR, where researchers are trying to understand the effect of superconductivity. I trust most of the people are aware of superconductivity, but if you don't know, don't worry. I am sure they will tell us what exactly the superconductivity is. So with me today are Argo, Rishabh and Preetham. All of them are research scholars, young research scholars in the Department of Condensed Matter Physics and Material Science here at TIFR, and they work in the superconductivity lab. And now let's hear from them what they are going to tell us. So all yes, guys.
Yeah. Okay. So in this lab, we try to understand materials properties, why materials behave as the way they do. And to know it, we have to understand how electrons are arranged in that material, because that gives rise to its properties. Basically, in this lab, we mostly work on superconducting materials. So these materials are extremely important. Their characteristic is that all of the materials are have resistance. Okay. So yeah, so every material has some characteristic resistance or resistivity. And in these superconducting materials, they have the ability to transport current without any resistance. So effectively lossless transmission. And there are many more aspects to this superconductivity that you will know during the presentation. So first, before going to how do we study them, we'll show you how we grow these superconducting materials. We mostly grow thin films of superconducting materials to study them. And it's very exciting because when you thin down your material and confine the electrons in one dimension, various quantum effects come into play that gives rise to very novel properties. So let's go ahead with showing you how we grow superconducting thin films.
Okay. So what are you going to show? Like, how do you grow it?
Yeah, so we grow the thin films mostly using magnetron sputtering method and pulse laser deposition. So Argo will now show you.
Hi. Hi. Actually, the superconducting. Okay. So Rishabh discuss the the use. I mean, the actual motivation to do our research on superconductivity. The main, I can show the main two effects of superconductivity, which is zero resistivity and Meissner effect. That okay. So zero resistivity mean you can show at the particular temperature T equal to 4.2, we can see the resistance goes from 0.15 to 10 to the power minus 5 ohms. So it is effectively the zero resistance, and also the Meissner effect, that is repel the magnetic field lines. Okay, and we will discuss this later on. Let's see how we grow the thin films and why we grow the thin films.
But I have a doubt.
Okay.
So Rishabh said superconductor has a zero resistance.
Yeah.
And now you are saying the resistance is of the order of 2 micro ohm.
Okay. So
what is it?
Yeah. So okay. In practical thing, we can't measure something zero. I mean, we are going to -5 or -6. In our lab, mostly we are going to 10 to the power -3, I mean milliohms. So that is effectively 0 for us. So in more accurate experiment, we can go 10 to the -7 ohm. We can see but always there is some normal in other side. Some resistance we can get.
Saying is what you are reading as a non-zero is actually noise. Is that correct?
Yes, actually some noise because we can't avoid the practical noise. Interesting.
So it is actually zero, but
Yeah,
you get some non-zero signal, and that is noise.
yeah, okay. Mainly the thing. So okay, so we will grow the film, the thin film, using scattering technique, using evaporation technique, and using pulse laser deposition technique. So the evaporation technique. It is the evaporation chamber I am showing you. So in the chamber, we can go up to 10 to the power -5 millibar pressure
So
at
what
a
do
low
you
pressure.
evaporate in?
Okay.
Is it some liquid or is it
No,
some solid?
yeah. So you know the tungsten filament in the light bulb. You all know it. And when we pass the current, it glow. Okay. So now we are using the same tungsten coil inside, and we are putting the material like silver. Silver is a superconductor, but I am just showing that. Or lead. Lead is a superconductor inside the coil. Then when we turn on the power through this, the coil
So
then
is it like a rapid heating of your material?
yeah, rapid heating and evaporate it just like water evaporation. Yeah, but we can't grow all the superconducting thin film using the evaporation technique, because here we normally boil the thing, I mean just evaporate the thing, but some material have very high melting point. Okay, so they interested to use evaporation technique for that type of material. So for that type of material, the easiest technique is the sputtering method. Okay, the sputtering method is we have a superconducting pallet, and inside the chamber obviously we need the low vacuum because we don't want any air molecule like, yeah. So we need a very high vacuum. Here we can see the argon is flowing and we can see the pressure is 10 to the power -3
Okay.
torr. Okay. And
so
yeah.
am I right in saying that before you actually grow the sample,
Hmm.
you evacuate this chamber to a very low pressure?
Very low pressure, yes.
And since you can't do the evaporation in vacuum, you are passing an inert gas.
Sputtering.
You are passing an inert gas.
And why we're passing the inert gas? Because here we have a target superconducting pallet. Okay. And here we are apply some high voltage, and in the high voltage, okay, so in the pallet we are giving some negative voltage. So going on. Oh. Continue. Okay. So the superconducting pallet we are giving some negative voltage. So when we use the negative voltage, some electron, obviously we throw the electrons here actually. So electron and argon collide there. And for the argon ions, argon positive. Okay. The argon positive are attacking the superconducting pallet because this is at negative voltage. So positive attack to negative, which is the attacking the superconducting pallet, and then from the superconducting pallet there is some it is going to that side here. The superconducting film is growing here. Okay, so obviously you can see the whole process. Okay, so that is all.
So how will you monitor the thickness of this film?
Yeah, okay. So okay, so we have to control the pressure. I mean, we have three parameters. One is pressure, one is the power, how much power I can give in
Sorry to
between.
barge in.
Yeah.
Actually, we had a network issues, but now the network is restored.
Okay.
So can I go back to the original network? So just for a moment, there will be a disturbance.
Okay. ये आपका चालू हो गया नेटवर्क?
Okay.
Okay. हाँ, तो so in the sputtering, we can grow some atomic layer, something from 5 nanometer to a micron level, something 100 of microns, 500 micron, 100 of nanometer, 500 nanometer, 1 micron. We can grow some thickness like this, and we have three parameters to control. One is power, the power between anode and cathode. One is the time, how much time I can turn on the plasma, and one is pressure. So via these three things, we can control the thickness. So much more time, if the plasma is running for a much more longer time, then we can grow the thick film. Also, if the power is very much high, something 200 watt, 200 watt or 250 watt, the thickness of film obviously increasing. So that is how we control the thickness, and we have our another system which we can measure the thickness in nanometer. Okay.
So what is the typically growth rate in this system?
Yeah, so typical growth rate, if I use 200 watt, the sputtering power, if I use 200 watt, then the growth rate is around 60 nanometer in 60 seconds. 1 minute, so 60 nanometer in 1 minute, typically. Obviously, it is depending on the power, on the pressure I have set here.
Do you have in situ monitoring system to measure the thickness?
No,
or you have to grow the material?
yeah, so in this system, we don't have in situ measurement system. We have to take out the sample from here. Okay, after growing this, after the pressure comes to normal, we have to take the sample from here, then grow in some another system, measure some another system, and then we can know the whole thickness. Okay. So now we can show the PLD. Yeah.
Your video was lost.
Okay.
We'll have this part. So this part,
from the beginning of sputtering.
Please repeat the whole thing.
Okay.
Sputtering part, please repeat the whole thing because there is no video.
Okay.
Yeah.
Okay. So
So we will start from the beginning, no?
Yes, for that question.
okay.
For that,
Okay.
here.
Okay. So in the sputtering system, we can grow several type of material. In the evaporation system, we can only grow some material which have a low melting point, so that it can easily evaporate. But some material have very high melting point, then I use the sputtering system. So what is the sputtering? It is mainly a superconducting pellet we have using, and the another position we have some substrate in which the thin film grows. Okay. So we are using argon, because argon is an inert gas. Then we have apply some power between anode and cathode, so that from the negative anode, some electron going to this chamber and react with the argon. So electron and argon, they are colliding and making argon ion and some more electron. Okay. So that is then we have argon ions, argon positive and electron in the system. And also the target, the superconducting palette in the negative position, I mean in the negative bias. So the argon positive attacking the negative bias, obviously it is the obvious reason. So negative, so positive ion attacking the negative superconducting palette, and from this the collusion, some material from the palette comes out, and we deposit that plasma to substrate, and we can make the thin film. So we can start.
Deposit only on the substrate, or it will deposit on the
Okay, so no. It is depositing the whole area. Something we can show the area. If I place some substrate there, it deposited on the substrate. Otherwise, it is deposited the whole area, obviously. So here you can start the thing, and you can see the plasma of the superconducting material niobium, because here we are installed the niobium. Okay, so yeah. So it is the blue plasma we are seeing. It is the plasma of the niobium. So now we can see, if I, yeah. So so there is a shutter. We just open the shutter, and you can see that is the it is the position of the substrate. So here we can place a substrate, and this plasma going this side to this side and deposited on the substrate, and we got a thin film. Okay. And now obviously it can grow some nanometer to some micrometer thickness thin film, so some atomic layer to many atomic layer, we can say. And we can also control the thickness of the material by using the how much time it is the plasma is going to the substrate, or how much power we can using between anode and cathode. It is the one of the simplest technique to grow any material, because here we just need some argon ion and one superconducting palette, and a power supply and a controlling unit which can control the gas. So that's it.
And also it's very compact.
Also it's very compact, because here only the pump is running.
In a 1 meter by 1 meter footprint.
Yeah. So we can go up to 10 to the power minus 6 torr. Okay, and the atmosphere is something 1000. We can see. So we are going to very, I mean, we evacuate the chamber so that no contamination because of the air is happen on the film, because it is obviously decrease the quality of our film. So yeah,
you're going something particular right now in this?
Okay. So if I grow something material, we are using from niobium nitride material. Okay, so for a better film, obviously we have to select a particular pressure, particular power, and particular time. Okay, so that is we have to always check and monitor the thing.
So you have to optimize.
We have to optimize every time whenever we start any new experiment or any new material.
But initially you said you put inert gas, and now you said nitrogen. So is it
Okay,
possible to have some kind of a chemical reaction in the?
Okay, so here actually for niobium nitride, we have to push nitrogen here. So in the same gas inlet chamber, we can see here. From here we can pass the gas into the chamber. So in this line we can throw the nitrogen and the argon. And obviously, if I need only niobium, then we can throw only argon through this line. And it is line we can.
So you have a choice of gas.
We have a choice of gas.
Nitrogen is also inert, right? So how practically inert?
Practically inert, but not like argon, because argon here actually argon is a very big molecule.
Nitrogen is that way less reactive.
Okay, so
but it seems to be also very fast, right? I mean, apparently you are growing the sample in less than an hour's time.
okay, no. That is not correct, because we have to go to 10 to the minus 6 vacuum. Okay, and if and now it is then the room temperature. You can see the temperature is 29. Yeah, it is 29. So it is very it is room temperature. If I go to 600 K, then it takes time, because when we heated the chamber, there is degassing, something degassing is going on. So then we can see after some time the pressure is increasing. Then we have to wait some more time, I mean some more hours, to get the 10 to the minus 6 or 10 to the minus 7 vacuum. So
it's not that trivial, in short.
Yeah, so it's need time, but the system is very easily understood, but it need time. Okay.
So
So
now you have grown the sample. So what next?
so what's next mean it is one growing technique. Okay.
Can you just take it out and put it into some cryostat, or you need to kind of
Okay,
take
so
it in
far
controlled atmosphere?
no, for niobium thing we just take it out in the air. So it's
Yes, it's nitrogen.
yeah. So for niobium nitride or niobium film there is no problem, but there is but maybe Rishabh can show you some other technique when we can take it. We can some sample we don't have to expose on the air because of our another experiment. So Rishabh will explain you that section. So, but in the niobium nitride there is no problem.
So you can take the sample out in the air.
We can take the sample out of air, then we can measure thickness, we can measure the transport properties and other things easily. Yeah.
Okay.
So
Now,
now the PLD Rishabh can explain you.
that is pulse laser deposition, right?
Yeah, so this is another growth technique that we use to grow superconducting materials in our lab. So the main idea of this pulse laser deposition, as the name suggests, is to bombard a target with the pulse laser. Here is our laser. This is a KrF excimer laser which has a wavelength of 248 nanometer. Okay, it falls in UV region, ultraviolet. So we pass the laser. The laser is then deflected through this material and then goes into our chamber where we carry out the deposition process. Okay, so the main idea behind this pulse laser deposition is that you have a target. Okay, the material that you want to study, you make a very thick target out of it, and you want to grow thin films. So you bombard that target with this focus laser, and it deposits energy within some top layer of the target, and then the target is then ablated out, okay, onto your substrate where you then can grow thin films. So for example, our target is so the target material is stuck on a pellet which is kept inside. This is a vacuum chamber. Okay, this is currently at approximately -6 millibar pressure. So let me just show you how we do the laser. If you can come and focus on the chambers. Okay, so you can see that we have multiple targets here. This is the sample holder which I am currently moving around. Okay, here we have our substrate onto which we grow thin films. Our targets are on the opposite side of it. There you can load multiple targets at same time. So laser is then passed tightly through this. Yeah.
What we are seeing is the laser shots.
Yeah, what you are seeing is the pulse laser shots that are striking the target, and then that is ablated directly onto your substrate for the deposition. This is carried out in vacuum, obviously, because otherwise the ablated material will then interact with whatever the gas is between your target and your substrate. So it is evacuated to a very good vacuum, and then this process is carried out. If let me show this again, in case if you missed it. So there are many aspects to how to control this deposition process in this pulse laser deposition. One is, for example, the frequency of these shots. Okay, this is currently at 2 Hertz. You can set it to something higher and then can control that. Yeah, I hope you can see the
we see that the frequency has increased.
Yeah, the frequency has increased, and if you can see the plume that is coming out from the target material. Okay, so another aspects to do it to control the parameter is obviously the energy of the laser that you target, etc. So this ultraviolet laser is used basically because the penetration depth of ultraviolet is very low, okay, in the material. So whatever energy that you are focusing on the target will be absorbed only in the top layer of your target, okay. Then that so you deposit the maximum amount of energy, and that will get you ablated material out, okay.
So
This yeah. So
efficiency of ablation is something what you're saying, that ablation.
yeah, UV is chosen for that, to for the efficiency of ablation. Yeah, next, so these are our mostly two main workhorse of our lab, where we grow thin film
sample growth.
For the sample growth. For measurement, we have multiple setups, and now we will go into that.
Okay. Yeah. Do we have any questions? Yeah. Well, let's have a look at the questions. Okay. Well, only technical questions regarding video. So, all right. So now, Pritam, you are going to tell us
Yeah.
about how you
Yeah, I'll be going to tell us about, we have first deposited our samples. The samples are now prepared, but for that grown samples that are superconducting or not, we have to test it. So for how we are going to test it, I'll show you that. So let me start with this.
screen share.
Share, yeah, from here. Yeah. नीचे नीचे नीचे. ये तो टच कर. Did you share now?
What?
So I'll be showing, like, first we for superconductivity, we know that we need very low temperature. So for going to low temperature, we need some cryostat that can go up to very low temperature. So here I'm showing you that here is a helium divat, that the liquid helium is around 4.2 Kelvin. But we can, by pumping over the liquid helium, we can go up to 2 Kelvin. So here's the basic setup of our continuous flow cryostat. Helium is getting flow from this tube to via this small cryostat, where the helium is 4.2 Kelvin. But by pumping over the liquid helium, we are basically doing the minimizing the vapor pressure by lowering down its boiling point. That's how it can go to 2 Kelvin. So from room temperature, we can go to 2 Kelvin for do our measurement and to check the TC of the superconductor in between 300 to 2 Kelvin. So for superconducting being a superconductor, as Rishabh has described, that it has basic two properties like zero resistance and Meissner effect. So for measuring the resistance, we do 4-probe kind of measurement. So we pass current from these two leads, and we measure voltage from these two leads, and we check the resistance. So when a particular film is superconducting, so below a certain temperature, its resistance should go down to a 0 ohm. So I'm showing you the plot where I'm plotting the temperature versus the resistance. So you can see here the resistance is going to 0 below a certain temperature. So here one thing is established, that the superconducting film we are growing, it has a 0 resistance below some certain temperature. So here for 5 nanometer NBN, we can see that the TC of that particular sample is around 11 Kelvin. So here I'm showing a particular photo of our sample, which is in Hall probe geometry kind of shape, and we measure in our RT probe that I'll show you later. So another is the Meissner effect. So what is Meissner effect? When the superconductor becomes superconductor, it becomes perfect diamagnetic. So when we are putting that particular film or that particular material in a magnetic field, it should repel all the magnetic field. So that is the basic idea of Meissner effect. So taking that Meissner effect into account, we do a two-coil measurement technique. So first we send some current through our driving coil. So what is a basic kind of solenoid? So it can generate some magnetic field. So when the TC, when it's above TC, so the film here, the sample is not superconducting. So all the magnetic field is developed by this drive coil. The pickup coil will pick up all the magnetic fields. So at that particular above TC, you can see here the magnetization that is in the nanohenry order is higher. But when it below its TC, when it becoming superconducting, it is repelling. I am showing here with the blue tick lines. So it's repelling most of the magnetic fields. So below TC, as it's repelling all the magnetic fields, so the pickup coil here will take a very small amount of magnetic field. So you can see here below TC, it's directly going down and it's very negligible for our measurement. So here are the two techniques. One is resistivity measurement and this two coil measurement technique. We can establish that our superconducting films are being formed.
Is it correct to say that perfect diamagnetism is a hallmark of superconductivity?
Yeah, so it is a perfect diamagnetism. Here we are actually using that property to measure. We are measuring that property that the it's becoming perfect diamagnetic below a certain temperature. That is, we are calling it superconducting transition temperature. So we are right now, we have talked a lot about how his film is grown and how we are doing this measurement to establish it's a superconducting or not. But I should also tell you what is the basics of superconducting, what is the theory behind it. So at around 1911, first Camerlingons, examined that the superconductivity they have first demonstrated. But after 50 years of gap, at 1957, Bardeen, Schuffer and Cooper, they have developed a theory for superconductivity. So here, let's say it's a lattice. I am showing you here. So whenever electrons is coming, here electrons are coming from this side. So at below its certain temperature, and that superconducting is very general to say that it should be very low at temperature so that the atoms are rest in their positions. Because when I'm having higher temperature, the atom will be vibrating. So when an electron will come, it will be scattered. So scattering means we are getting some resistance. So for giving rise the phenomenon of superconductivity, so it should be have very low resistances. Very low temperature. So at low temperature, what happens? These atoms will be stabilized in their position. So when an electron will be coming, so it will distort these atoms. So atoms, we know when electron is coming, so it will be forming some positive charge and it will call it phonon. So this first electron that will coming in the lattice will distort these atoms and form a phonon, and the next electron that is coming from opposite spin and charge, opposite spin and momenta, will see this phonon and this will form a Cooper pair. So electron, phonon and electron, this bonding is called a Cooper pair. So, and this Cooper pair can give rise to this superconductivity which is flowing, and this Cooper pair will go through this material without any scattering. That's why you are getting superconductivity at lowest temperature. So here I am showing you the lattice spacing is around 0.1 to 0.4 nanometer, but this Cooper pair or this interaction length can be around hundreds of nanometer, which is giving rise to this superconductivity. Then if I am saying with this above TC, all the materials are behaves like normal metal or semi-metal or whatever it can be. So here with the red line, that is normal state, I am showing you the density of state versus with terms of energy. So it should be a flat, like I'm showing you in the red line. But when it becomes superconductor, so when this Cooper pair is formed, so around below this minus delta to plus delta, all are Cooper pairs. There is no electronic states available. So here in the superconducting density of states below its critical temperature, only we can have, there is no electron in this gap. So there are only condensed Cooper pairs. So there, if we can do this measurement, like to see, is that this is from a theory I'm saying. So we have to do something to visualize this as in our experiment. So for that, we have an experiment that we can do is tunnel junction. So for understanding tunnel junction, we first understand what is tunneling. So for quantum tunneling, we can say that if I am throwing a ball or a huge ball in a wall, it will definitely always come back to me. But when there are tiny particles like very small particles electrons, they have a finite probability that they will go through that particular wall. So this is the basic concept of quantum mechanical tunneling. So And what I have showed you, the gap, that gap can be realized through this quantum mechanical tunneling experiments. So for that, we can develop these tunnel junction kind of junctions, and here we are using NBN, and then we develop an oxide barrier on it, and then we deposit Ag as and with this geometry. So here the green strip lines is our NBN, and then this yellow strip lines is our Ag, that is the silver. So by forming this kind of junctions, we can visualize this tunnel. So as I showed you, this is a superconductor density of state, and this is a normal metal, and in between this there is a insulator that is working as a vacuum. If we are going to do STM, that will be described later. So when in normal metal, electrons can go from this region to this region, and but electron can't go to this region. Even it can go from this region to this region. So when we are doing this experiment, like we are in this particular energy, then when at the zero level, this is, let's say this is our zero. So from zero, when are we increasing our energy by tuning it to some voltage, because electron will take up that voltage as EV. Then it will first, there is, with increasing voltage, there is no change of current, because there is no state to flow from this region to this region. But when we are increasing that particular voltage, that means we are giving more energy to our electrons, then there is a state from this region to this region, or this region to this region. It will give the resistance will come into picture, and with increasing voltage, the current will increase. So if we differentiate these particular IV characteristics numerically with respect to V, we'll be getting this kind of conductance plots. So here, and we can see between some particular value to particular value, there is zero conductance. That means there is no states available, as I have showed you from the theoretical curves. And then there are similar kind of superconducting density of states is available. So in this way, we can visualize what is the superconducting density of states in a superconductor. Then also there are different experiments that can give you what is that can also give you the particular properties of the superconductor and also the superconducting gap. So one of the experiment we do in our lab is the point contact spectroscopy. Here there is a tip and there is a substrate or sample. So we first with this particular worker, we move our sample, the tip towards our sample, and we just directly make a contact in between them. So by making this contact, we can have different properties of that particular superconducting film. So I can explain in very short that when an electron is coming from this region, then it is seeing there is a density of states available. But when when an electron is coming in between this to this region, then it is repelled, it is facing the wall and it is going back, and it is leaving a Cooper pair in the superconducting region. As in the superconductor, there is only possible to go as Cooper pairs. So what happens, like and Cooper pair has 2 electrons, I have said. So the charge doubles, then the conductance also doubles. So in this plot with theoretical spectra, we can say that at the normal region, like this region, this is around 1, the normalized conductance. But when in the superconducting region it is going, but like in this region, the conductance is becoming double. But in general, it is very difficult to realize practically to make a junction which is very clean and to get a double of this conductance plots. Pointers, okay, point. So with this doubling of this conductance for plots, sorry. So yeah, so in a practical purpose, we can't get a very practical, transparent junction that can give us this kind of spectra. So what happens, like due to some oxide layer on the top of that particular sample, or some other effects of multi-gap superconductivity, or some other effects, we can get, we are actually practically get this kind of shape in our experimental spectra. So this is so this is a real data I am showing here. So when a junction is formed, it can give you many kind of spectra. So I'm showing you for different resistance versus the how the spectra will evolve. So here I can show you that this is a spectra, but that is not that much good. So we are getting some effect of critical current over here. But when we go to some higher resistance, we can go to some ballistic, we can establish a ballistic regime contact, which can give us some information about the superconducting density of states and its gaps. So also we can say that, as I have told you earlier, that it has a critical temperature. That means the gap and the gap arises due to this superconductor Cooper pairs forming. It should vanish. The gap should vanish at the critical temperature. So for realizing that fact, we take this data with the temperature variation. So here you can see that this gap is coming down with this temperature, and it's going to be a flat one around Tc. So if we take out some information and extract some data from this, and we can show that these are our delta, that is a superconducting order parameter or superconducting energy gap, that is varying and going to 0 at a particular temperature where the superconductor vanishes altogether. That is the critical temperature of the superconductor. So this much I wanted to show here for my basis. And then there is also one experiment called scanning tunneling microscopy. There you can also visualizes the density of states of the superconductor. So Rishabh will tell you about
Why
that.
is it that the energy gap kind of saturates towards lower temperature? So from TC it is increasing.
Yeah.
But then as you pull the sample further, it seems to kind of flatten out.
Yeah. So this is the key, that for forming the Cooper pair, the phonon electron and phonon interaction should have some basic energy. So when we when we lowering the temperature, that gaps first increases, but below certain temperature, it's altogether stabilized, because maximum that much energy can be provided at that particular temperature. So that becomes constant after certain point. So so that's why it is getting stabilized at some temperature, and it is constant altogether. So any more questions?
Yeah. So what we can do is we can take a look at the YouTube and take
Okay,
the session.
okay,
So
okay.
if you can stop the slide share.
Yeah, I have stopped the slide share.
Let me read the questions from YouTube. Okay, so well, right now we are not seeing any question.
Oh.
Oh yeah. So why was the substrate holder? Maybe I think Rishabh, you can take this
Yeah,
question.
so the question is, why was the substrate holder oscillating in the PLD setup? So the reason to oscillate the substrate holder while we are doing ablation is to effectively. Otherwise, what will happen? Yeah, sorry. Yeah, so the reason why we use oscillating substrate holder is to effectively use the entire area of target. Otherwise, what will happen is that laser will be focused on one point and ablation will be occurring only from that point. In order to effectively use the entire target area, as the ablation is going on, we also oscillate our target back and forth to utilize the entire area and to utilize it completely.
Okay. I think Pritham, there is one more question pertaining to what you just explained.
Okay.
So the question is, can electron pairing in superconductors be derived from the presence of the real space states of the electrons?
No. So from actually this
Or do you think this is a very hyper technical question and not really at the China level?
yeah,
Okay,
that's fine.
Yeah. So we suggest you please write us an email and we'll of course answer this question. This China is actually not really for experts, it's for the novice, so to say.
So but I want to show you the basics, like where we do these kind of experiments. So these are our inserts, like where we put our samples. This is our two coil setup. If you can zoom it to there, like I have shown in the picture, but this is a real setup. So these are the two coils, and one sample is sandwiched in between them. So in this way, this hole insert, and this is an RT insert. So our sample is sitting here, and these are the contact pads where we do the 4 probe contacts. And this small insert, like this height only, this goes to here in this cryostat. This is a very small cryostat, and this is very compact one. Like from this divar, this is our helium divar. From the divar to we take this helium through this tube. If you can show them that this is a very small cryostat. So if you can show that this is a very small cryostat, so by which we can go down to 2 Kelvin and checks what needs to be checked. So that's all I wanted to show from my side. And now Rishabh will gonna tell you what next about the scanning tunneling microscopy.
We go inside now. So, go ahead. Are you going to take us to the STM?
Yeah, the scanning tunneling microscope.
Okay, so now let's
I'll
see.
tell you how we can see atoms actually. Come. Yes. Yeah. So this is our scanning tunneling microscope lab, and before I show you the instruments, I will take you through what this microscope is about. Yeah, so now I'll tell you about the main workhorse of this lab, the scanning tunneling microscope, and how can we use this microscope to image atoms. Actually, we can visualize and see how atoms are arranged in a material, and that is an extremely powerful technique to understand our basic goal that I have said in starting about why the materials behave the way they do, and how do we actually probe them. Yes, so the scanning tunneling microscope, wait a second. Yeah. So this is a way to see the atoms. And what is the size of atoms? Atoms are usually of the order of one or of the order of angstrom, that comes around 10 raised to power 10 meter. That is 10 raised to power minus 10 meter. That is extremely small. But this instrument, this STM, is not just, just to see the atoms. It can tell you more, and it is a really excellent tool to probe the electronic properties of material at the atomic level. So whatever you have seen just before, those techniques actually probe the material as a whole. Okay. But using this, you can see what is happening like in the spatial, with the spatial resolution of atoms. So this is not your usual microscope. Okay. So in your usual microscope, you focus light on a specimen or your sample, and then you magnify it to see how things are arranged in the sample, or in biology, you try to see some specimens, etc. So the wavelength of that light is usually in some hundreds of nanometer. Okay. So that gives a fundamental limit as how much zoom you can have in a microscope by just simply using optical means. Okay, we have to surpass that in order to see atoms, because they are 100 to 1000 times smaller than what you can achieve in a normal optical microscope. So we revert, rather than using photons of that high wavelength, we use electrons here. Okay, so these electrons can have a wavelength that's smaller, and that's what we utilize here to see. So directly imaging atoms with the beam of electrons is actually a different type of microscope, that is tunneling electron microscope. We are not talking about that here. I will show the scanning tunneling microscope now. So the basic principle on which this microscope works is quantum mechanical tunneling of electrons. And as you have seen what quantum mechanical tunneling is about, but I will give you a very small primer right now. So in classical mechanics, for example, if you have a barrier, okay, let's say a wall in front of you, and you have energy less than that, if you have energy greater to climb up the wall, you can go past it. Okay, you can effectively go over the wall to the other side. But if you don't have that much energy, you can't go through the wall. Okay, you can't walk past the wall. Classical mechanics prohibit that. But in quantum mechanics, if you are a quantum mechanical particle, there will be a finite probability of your existence on the other side of the wall, and this is what we rely on. Okay, here the quantum mechanical particle is electron that we utilize, and we will talk more about this barrier, etc. So how do we achieve this using this quantum mechanical tunneling to probe things at atomic level? First, to see things at that spatial resolution, you have to have a very extremely sharp probe. That we actually form here. We use extremely sharp tip, a metallic tip. You can see here a picture of one which is electrochemically etched tungsten tip. You can see how this is extremely sharp. Okay, this is first requirement. Second is the quantum mechanical tunneling of electrons. Now, this quantum mechanical tunneling of electrons can happen only at a very minuscule scale. Okay, so this probability that I talked about to go past the barrier actually decreases with the width of barrier, and hence you have to be extremely close to your sample in order to facilitate this tunneling. So, for example, here is our tip, and the barrier that I talked about will be vacuum in this case. Okay, electrons can't just simply go through your tip to your sample or your sample to your tip. But if you bring your tip down to order of nanometer, they can actually quantum mechanically tunnel through tip to your sample, and this current that will come out of this electron tunneling, which is the effective measure of how many electrons are going from your tip to sample, is usually extremely small, of the order of picoampere to nanoampere. Okay, this is extremely small to directly measure. So a lot goes on into this microscope, and we will see how to, how this instrument works, how to actually do this. So first of all, as I have shown you that your tip has to be of the order of nanometer level away from your sample. Okay, you have to, you can't just do that normally. You can't just hold a tip and bring, extremely close to your sample. Because your hand will be vibrating, there will be vibrational noise, there will be electrical noise in case if you want to detect signals that small of the order of picoampere to nanoampere current. So for that, we have to provide extremely good isolation. So isolation is of two types. First is vibrational isolation, in which our entire STM setup is floated on a vibration isolation table that basically uses a pressurized nitrogen gas to effectively float over these legs. Okay, so this reduces the vibrations that will be coming from the ground and going into your STM. You effectively decouple your STM chamber from that. Second, you have to remove the electrical noise. Now, all of you must have heard about something called as Faraday cage. Okay, so in a Faraday cage, if you basically cover your, for example, mobile or any electronic equipment with some metallic mesh, or let's say aluminum foil even. Okay, that can work. So there will be not a signal outside because this mesh, the electrons in this mesh or this metal will arrange themselves in order to cancel out whatever electrical interference that is coming from outside. Okay, across various frequencies, your radio frequency and everything. So we keep our STM setup in a shielded room that.
So you're basically trying to protect it from external electrical influence
As well as mechanical
or
influence.
external mechanical influence
Yeah.
like ground vibration. And
Yeah,
for
totally.
protecting, for isolating the system from mechanical vibrations, you are keeping it on a floating
Yes.
platform. And for protecting it from external electrical disturbances, you have built a Faraday cage. Is that right?
Yes.
Okay. So it's
And-
a very extreme technology in the sense that they must make sure that the system is
Yeah.
free from minute kind of external disturbances. So that is the reason that STMs are like kind of extremes of measurements. So to say.
Yeah. This is a how to say a pinnacle of a measurement to go to that
So
resolution.
I trust there was a Nobel awarded for this.
Yeah. So the first one coming from this is Binning and Roger from IBM Labs actually. So they first devised this method to get atomic resolution of
And this was perhaps
graphite,
in
etc.
mid-80s, right?
Yeah, toward the end of 80s. So that happened, and in the past, what now, 30 years or so, this technique has come actually much far. That nowadays, this is used to, for example, one uses to probe the states of your next generation electronics that you want to devise out of materials such as graphene, etc. So like seeing down to atoms gives you capability to understand what is happening there. Okay, and that's the USP of this
So
thing.
is it right? I mean, if I have to take a very colloquial view of it,
Hmm.
at extremely low temperatures, I'm
Yeah.
going to walk extremely small steps across a material and look at it at say the
Yes.
nanometer gaps.
Yes,
Is that right?
yes, sub-nanometer even.
Sub-nanometer and at extremely small energies.
Yeah, at extremely small energies, and I will come to all that. I will show you the entire STM room and all these things about vibrational and electrical isolation that I'm talking about. But before doing that, I want to take you through the levels through which you have to go through to build this equipment. So apart from isolation, so the next part comes like
Okay. So for viewers, please understand that building a STM is not a trivial task. It's highly complex instrument. And to say that as far as a laboratory scale instrument, the laboratory scales experiments are, this is an extreme technology.
so, and I'll show you all this in order to, so this isolation part is one thing. The another part was now to actually bring that extremely sharp metallic tape very close to your sample. So in order to do that, we utilize a series of things. For example, as Pritham has shown you in the previous setup, coarse positioner, that he has actually used a tip to smash into a sample. Now that's a different kind of probe, to look at how electrons are behaving in your sample. Here, our aim is not to crash. Okay, we have to have just to be in the limit to be able to like extremely close, but not touching the sample. Okay, you can't be far apart from it because then quantum mechanical tunneling won't happen. You can't touch it because then, your connection is short and that's a different kind of probe. In order to do that, you have to be extremely close and you have to maintain that. So first, how do you come that close to a sample? Okay, so this let's say you have built this isolation techniques. How do you go this through? So first is coarse positioner. Okay, so your sample, this is our sample holder, and this is a housing of STM where the main part of STM takes place. So you place your sample, and I'll show you this. So this is a coarse positioner that is first used to bring your tip extremely close to your sample. Okay, but it's still far away. You have to have order of nanometer accuracy. Sorry, better than that to come close. For that, we use the piezoelectric tubes. So piezoelectricity is the ability that certain materials, if you pass electrical current through them, they can mechanically deform. Okay, and we use that to our advantage. ठीक है. So using this piezoelectric tube, as you can see, this is separated into some segments. So this tube is then gold plated to provide good electrical contact to the entire surface. And when you apply voltage with respect to one part of the tube to another part, there will be a mechanical expansion or contraction happening. And you can use this to elongate it. You can use this to shorten the height. You can use this to bend the tip, etc. So first you come extremely close to the sample using coarse positioner, and then you use piezoelectric tube to go to that tunneling regime. And there, of course, the magic happens.
So you have a kind of a coarse approach and a fine approach using piezo.
Yes, a fine approach using piezo.
How do you get a feedback? How do you know that it has reached the nanometer position?
Okay.
Do you have any feedback mechanism?
Yeah, we have feedback mechanism, and I'll come to that. So one short way of looking at this is when you are far apart, well, even few nanometers to, well, anything micrometer, millimeter apart, you are not getting any tunneling current. Okay, since there is vacuum between this tip and this sample, okay, effectively your electrical circuit is open. You are not getting any current. As soon as you go into the tunneling regime, you will start that current starts to increase exponentially with distance, and that's when you know that you have reached to that level, and then you control it there. And coming to how to maintain it to that level, like you don't want your tip to then drift away apart or getting too close to the sample. We'll come to the electronics on how to control it. So this coarse position piezo tube is first used to bring the tip very near to sample, and when it is first, as I have told you, that the currents will be extremely small, ordering from picoampere to nanoampere. That depends on how close your tip is to the sample and what is the voltage applied between them. Okay, that voltage applied is basically applying voltage is giving energy to the electrons. Okay, that is measured in electron volt. 1 volt applied to electron will be 1 electron volt energy given to that electron. So the current is extremely small, and you have to detect that current, okay, apart from your noise. So first to amplify it, okay, and the amplification is nothing small. No, you amplify it to the order of 10 raised to power 9. That is extremely large magnification that you have to do. First, you get this current amplified, and then you detect that current. Now, that current tells you approximately that, okay, you are in tunneling regime. And then, obviously, the feedback mechanism. Now, suppose the case that your tip is near to your sample, but it's drifting. Okay, it's getting close to the sample, your current is increasing. You have to correct for that. Okay, you have to tell your piezo tube to retract a bit so that your tip will maintain its position with respect to your sample.
So you kind of maintain a constant value of tunneling current.
Yeah. That is our main mode of STM operation. And for that, we use a control electronics, a feedback control, which tells us if current is decreasing, it tells our piezo tube to expand to go to that level of current again. And if it's increasing, piezo tube contract. So this feedback mechanism goes on all the time. And that's how you keep your tip at a fixed distance away from your sample. Now, another aspect, as Pritham has told you, that we study superconductors in our lab. Okay, now these superconducting materials become superconductor at a very, very low temperatures of the order of few kelvins to tens of Kelvin. So for this, we use liquid helium, thanks to low temperature facility in-house in TIFR that provides us with the liquefied helium. So this entire housing that I talked about is kept in a cryostat. Okay, think of it as a bucket that holds liquid helium, except you can't put liquid helium directly out in open because its temperature will suddenly rise and it will evaporate. So you keep it dipped in this liquid helium, and then you use a series of pumps, etc., to do evaporative cooling. That is essentially same as why nail paint remover, if you apply on your hand, it will feel cool because it evaporates and takes away the heat from you. So liquid helium is 4 Kelvin, 4.2 Kelvin precisely temperature. So you use this method by reducing the vapor pressure, and you use a series of other methods using other isotopes such as 3 helium, etc. and we have a capability in our lab to reach sub-Kelvin temperature range. Okay, so in order to maintain, for example, all this, your sample, your tip, etc., all at same temperature, all this is kept in a copper housing. Yeah, so now I will come to the part of how do we image atoms using our STM. So as I have shown you that we set a current value, okay, that will fix the distance between my tip and sample, and my feedback is going on. So if that distance varies, it will correct for it, and I know what voltage my feedback is applying to my piezoelectric tubes in order to correct for the topography surface. So let's assume that you have atoms arranged in this fashion. Okay, so as you move your tip, as I've shown you, you can bend your tip by applying voltages across the quadrants. As you move your tip, on an electron is basically have a, so an atom has an electronic cloud over it. Okay, so you as your so tunneling is at the apex of your atom, the tunneling is higher, and when you go between your atoms, the the electron density will be lower there. Okay, so as you move your tip, you will the current will fluctuate. Okay, going from a center of atom to between atoms, and again, center of atoms, etc. And this will lead to the correction in piezo tube that will then move across the sample, basically tracing out how atoms are placed. And if the step comes, you can see it will go over the step, and this fixed current value. So measuring this voltage will give you a direct correlation with how atoms are arranged. And this is what we use. For example, here the material is niobium diselenide. Okay, as I have shown you the edge here. Now this sample has an edge at one edge, and if you go from this left hand side to right hand side, your profile Z that will come measure out like this, and you can see that it can see the step. Okay, now to further image these atoms, and I will show you the atomic image that we have captured in our lab here at TIFR on the same material, niobium diselenide. You can see this. So here, all these dots that you are seeing are selenium atoms. So this niobium diselenide is cleaved in situ to preserve its surface so that its surface is not contaminated. And then when you move your tip in this fashion, it gives you such an image. You can see the bar here. It's 1 nanometer, and you can see the sub-nanometer resolution that is coming, and imaging of atoms. And if you will see that along a line scan, if you take, you can see that the height varying as the tip is moving, going to atom, going between atoms, then again following the same routine. Now, one more thing which is very particular to this material is that you can see this sort of checkerboard pattern also coming alongside with this positions of atom. Now, this is actually the charge density wave. So in this material, the electrons, this is a property of this material, that electrons will place itself in such a manner that the charge is not uniform everywhere, and it is forming a wavy pattern. And that you see as this checkerboard pattern that is coming in this.
That is not because of the height variation.
No. This is not because of the height variation. This is actually coming because the probability of having your electrons here is higher than having them here. Okay, this is a material property, consequence of how niobium and selenium come together to form this material. Yeah. So we use this to probe superconductivity, as Pritham has showed you. The IV characteristics, etc. You can then measure because electrons are tunneling, and you can see the superconducting gap. Okay, so the gap comes because the electrons have formed Cooper pairs inside your superconductor. So at those very small energy scales, there are Cooper pairs in superconductor, but there are electrons, normal electrons in your tip. Okay, so they just can't tunnel through because on the other side there is no Cooper pair, there is no place to hold Cooper pairs. Hence your conductance dips. Okay, and then as you provide enough energy, you overcome this superconducting gap, and your conductance becomes comes to the normal value. So I will end this presentation right here, and I will show you the working of STM
So
lab.
let's stop the share and let's have a look at some questions. If
Yeah, if you have any questions right now, I can take that.
then let's have a look at the YouTube.
Other questions?
Okay. So is it possible to simulate the effect of reverse breakdown voltage of Zener diode and make superconducting material? No, I think this is quite an out of context question.
Out of context question.
I think he's already answered. He's already answered.
No, the superconductor is basically a different state. Breakdown of Zener diode will give you very high current, but that's not the point. The superconductivity is different.
I think that was. So let's have a look at the STM.
Okay, we will have a look at the STM. Yeah, so first of all, as I talked to you about isolation, both vibrational and electrical, this entire setup of STM is held in this shielded room, as I talked to you about the Faraday cage, to minimize the electronic interference that will come from outside. Okay, so this entire room is basically a shielded room. You can come inside and see all the walls, even the floor. Even the floor we have shielded. Okay. Now the another aspect of this thing is come inside. Yeah. So the isolation part that I was talking about. Okay. So this is a floating table resting on these legs, and we use pressurized nitrogen to then you can see. Okay. If you press it, it is hovering. Okay. So that's how you isolate. So the divar is kept inside that blue.
Literally floating.
Yeah. Table is floating on nitrogen gas. Okay, so you decouple it from any mechanical vibration that is coming from the ground, and for electrical vibration, you have shaded room. Also, these panels are kept in this entire housing. This is actually to minimize the sound vibration. So vibration not only comes from your ground, it can also come by the sound that is carried in the air, and these foams absorb that. So once the STM operation is going on, we close this door, and this door is entirely completely isolated, both mechanically and electrically from outside interference. Now this divar is used to cool down the temperatures down to sub-Kelvin range, and here you can see the preamplifier part that I was telling you. We have to amplify to the order of 10 raised to power 9 in order to measure the tunneling current. So right now I have kept the main STM part outside, and I will show you this. Yeah, so this is our STM housing. Are you able to see it clearly? Let me shine light on it. Okay, so yeah, so this entire thing, all this setup, these are called as radiations, etc. Now all this is a part to cool it down. The actual STM part is happening down in this very small range. Okay, this is your 1K port. So basically helium, we keep a very small reservoir inside to pump over it to reach less than 4 Kelvin range. And but the actual STM operation goes around this. Okay, so this, as you can see.
Can we have paper in the background? So that.
Yeah, all right, we can have a paper in the background.
Yeah.
Yes. Yeah, I think it's not focused. Yeah. Yeah. So I talked about coarse positioner, that is this part, and I will show you how it moves. Then I talked about the fine positioning of my tape that happens with this piezoelectric tube.
You can release the paper. I'm holding the paper.
Yeah. So this piezoelectric tube, as you can see, it's separated in quadrants. I don't know if you can see that clearly. Yeah. So
this is out of focus, so it will keep focusing between your finger and thing.
Okay.
No, all right. I think people have got it. People
Yeah.
have by and large got it.
Yeah, so fine. Yeah, so this is the piezoelectric tube that is used for fine positioning, and this is the coarse motor. I'll show you the operation of coarse motor. Okay. So coarse motor, as Pritam has shown you, moves by the application of voltage. Now each step that you take is extremely small because you have to, each time you move extremely in small steps towards your sample. So showing just one step won't get recorded on this camera. So what I will do is I will apply this voltage uh, from this unit that will control this Walker. So let me just set the amplitude.
This
So-
is your piezo control electronics?
No. This is not the piezo controller. This
motor
is
control.
motor control, the coarse positioner. Okay. So I am applying some, let's say 35 volt at a frequency of 301 hertz. Okay. So if you apply it, you can see the movement happening in this manner, and it will show you how. So instead of one step, I will be taking 301 steps per second.
Okay.
Okay. So that's the
It will come down to this some software issue.
Okay, so that's the part. Let me show. Yeah, what you have to focus on is the hair. Okay, you just look at this particular part. Just look at this particular part here, because this will move. The bottom part is stuck to the bottom plate, and the upper part will move, carrying this entire assembly upwards. Okay.
Yeah,
Yeah,
see the
you
gap
can-
widening.
Yeah, you can see the gap widening. Now this is 301 steps per second. Okay. During our approach, while going near the sample, we do this one at a time rather
Yeah.
than 300. Yeah,
Okay.
so this is one part. So our sample actually, so one version of this is this. So this entire setup is then kept in a housing of copper, okay, to keep the temperature same throughout our entire apparatus. And our sample, which is this holder, this comes from the top. We can load it from the top, that will go in. And then the entire housing that I've shown you works in this particular
Right.
part to get to the tunneling
How big
regime.
can the sample be?
Huh?
How big or how small the sample has to be?
Yeah, now that depends on your setup to setup. Okay, since this is a very local probe, we don't require too large a sample to probe it. Okay, we see down the so this our sample holders can carry up to
Let's say
roughly
about 8 mm dia.
yeah 5 mm usually
5 mm.
5 mm sample, 5 mm in diameter thick sample. But since we probe extremely small parts of it, that's more than large enough for our case.
So in a 5 mm, approximately 5 mm diameter, roughly sample,
Yeah.
you are looking at the most few micrometers.
Yeah, but as I have shown you, we can bend our tip. Okay, so it's not like we will just probe only on one part.
So
We
you
can
can-
move it
okay,
across,
okay.
and now those things depends on your electronics, and we can cover an entire area to look at various positions. The control electronics that I was talking about is this entire unit. Okay, so the current from this tip goes through the wires coming out from the cryostat towards this electronic unit. And this is what controls the feedback mechanism.
So this
Okay.
is your STM control electronics.
Yes, this is our STM control electronics. And then we can monitor and control our STM by sitting outside because
You
because
can't
of
go
the
in.
yeah we can't go in. The moment your tip is in tunneling regime and we go in and strike that, you are done. Your sharpness of tip, your tip will crash. Okay.
Experiment is over.
Yeah, experiment is over. And believe me, it's hard to keep that
Yeah,
tip
yeah.
intact. Okay, so we control it.
All the ones who have worked in low temperature regimes,
Yeah.
they can understand the complexity very well.
Yeah, that happens. So we control entire things from out here. Now, I can take some questions if there are any.
Yeah, maybe you can show us some pictures of STM,
Uh,
example pictures, more example pictures.
yeah, but no, what I will show you is one particular type of experiment that we use STM to probe,
Okay.
and that is vortex dynamics, and I will show you a glimpse of how exciting that can be.
Okay. So can we see that now?
Yeah, we can see that in the presentation.
Okay.
Yeah, so before I go to that, now as I have said that our samples have to be in pristine condition because we are probing atoms, okay? There can't be any oxide layer formed or some dust on the top of it. So whatever material that we make out in our pulse laser deposition or sputtering, we carry that to our STM by completely keeping our sample in vacuum. That is called as in situ vacuum transfer. And for this, we use this.
It's a kind of a vacuum suitcase.
Yeah, this is a
So,
vacuum suitcase.
Put
So
material in,
yeah,
in
we
vacuum at
yeah
some place,
we
carry it to some other place, and
we attach it to our pulse laser deposition. We make our samples, get that sample inside of this this housing, and then we can carry this directly to our
measurement setup.
measurement setup, STM, and that.
Okay.
Yeah, so this comes in extremely handy to maintain surfaces. Now I'll talk about one example of what type of physics we probe using scanning tunneling microscope. Oh, this is open.
You have to start the slideshow.
Yes. Okay. Yeah. Yeah. So we have talked about how your superconductors are sort of perfect diamagnet. Okay. It repels magnetic field, but there is something called as, so these superconductors are classified into two further subcategories. They are known as simply as type 1 and type 2 superconductors. So type 2 superconductors, so type 1 superconductors exhibits your normal Meissner effect that was shown to earlier in this presentation. In type 2 superconductors, above a certain limit, instead of expelling the magnetic field completely, wait a second, let me get the point. Magnetic field completely, my sample will then allow this magnetic flux to pass through it, but it's not passing throughout it. Okay, it's passing through it in the form of small circulating currents that is called as vortices, and these vortices that are then these vortices carry a quantized magnetic flux. Okay, it's not some arbitrary quantity. That flux is quantized, how much magnetic field is passing through each. And since a consequence of simple Lenz's law, if magnetic field is passing through a conductor, there will be circulating currents around it. Okay, now these currents are circulating and they form a vortex. And these vortices are what we can distinguish in our superconducting samples using our STM. And these vortices, because of these currents, they interact with each other. Okay, so they form a test bed to basically conduct experiments and study how materials, basically they are analog to arrangement of atoms now. Okay, they are interacting with each other. You can control their density, you can apply temperature to it, and you can study many things that are common with your normal matter, such as melting phenomena, etc.
So you have a wonderful tool to study phase transformations
Yes.
in real materials.
Yes, without actually studying real materials, but here we have more control over, let's say, density and how they interact with defects and everything else. So this is a test bed. This is called as vortex matter.
So you have greatly tunable and controllable test bed
Yes.
to study phase transformations in materials.
Yes.
Is that correct?
Yes. Yeah, it's so for example, in the same niobium diselenide that I have shown you the atomic image, there you can see the formation of vortices at this 450 millikelvin sub-Kelvin temperature at applied magnetic field of 20 kiloersted. Now this entire image is 500 cos 500 nanometer. Okay, now these are not your atoms. Okay, those atoms were sub nanometer range. Okay, as you can see, there are probably 10 of vortices in 500 nanometer. Okay, these are not your atoms. These are something different that actually acts as a soft matter system to study various things. So how do we image them using our superconductor? As we have shown you this gap. Okay, so from where the magnetic flux is passing, our material turns normal. Okay, that's no longer superconductor locally in that region. So there, our conductance, for example, is simply flat. It does not vary much with voltage, whereas our superconductor, the conductance will vary highly. So we fix the voltage between tip and sample to this point, and as there will be difference in conductance, that we record the current, hence by extension of it, the conductance. So we can see the difference in conductance where vortex is and where it is not, and that's how we can image them. And you can see a beautiful hexagonal ordered structure found by the vortices in this material. I'll show you one example of this phase transition. So in two-dimensional, the melting of material does not happen like your, let's say, simply ice melting into water. Okay, it has been proposed that they will go through something called as hexatic fluid between solid and isotropic liquid. Okay, and seeing this hexatic fluid is a very important physics to know, to uncover, and to study. And that's one example what we have done. Past, my seniors have studied this system. So we took very thin molybdenum germanium films that we have grown using the pulse laser deposition setup that we have shown. And here you can see that at 55 kilostar magnetic field vortices are there, but they are not solid. As you take images, for example, from 1 to 12, from each image, you can see that there is a little movement of vortices in this zoomed part. And in your regular liquid, what happens? Your atoms are free to move in any direction whatsoever. Okay, that's why it's isotropic. The liquid is isotropic. But this hexatic phase, one characteristic of this is not isotropic. This will only flow in the directions of your underlying lattice. Now, what is our lattice here? Our lattice is our vortex lattice that we are studying. And as I have shown you in earlier slide, it usually forms this hexagonal shape. So in hexatic fluid, it will move only in one directions. Okay, so we have three principal direction: one this, on the horizontal, and another this. All these at 60-degree angles from each other. So you can see in hexatic phase, they are moving along one direction only, and not like your isotropic liquid phase. So this is one of the case where we have used STM to study some material properties, or in this case, vortex material properties.
STM has proved to be a very powerful tool to study unusual phases of matter.
Yes, totally.
Okay. Great. So shall we have a look at the questions if there are?
Yeah, we should look at the questions.
Maybe you can stop share. Stop share. Yeah, and we'll go to YouTube.
Yeah. How do you classify the constituents of your scanned image? Okay. So how to know basically what atom it is that you are seeing?
Or to put it colloquially, how do you know what you see is what is actually there?
Yeah, what is actually there? So first of all, there are several other techniques that we know. For example, your XRD, your TEM, etc., that can tell you more about your structure of your sample, of your material. And this STM, we can look these atoms closely. Okay, now atoms are well, what you can match. How? Okay, for what you ask is I have to show you again the slides that we have to share. Wait a second. So let me just tell this orally then. What happens is that, okay, you know how atoms are arranged. You know what distance should be between those. You know what distance should be between those atoms at a given. For example, yeah, this. Wait. Let me go to the slide. Yeah, for example, this step height. Okay. Now, how NBSE2 is arranged, you know what a single layer of 1 NB and 2 SE atoms, what the step height would be theoretically, because you know the size, you know the structure of that. And from this, you can verify what is happening. Yeah, so these are the things how you can characterize how atoms are placed. And there is more to it. People use STM to basically manipulate atoms. Even you can pick an atom and make your own structures, whatever you want, a thin one-dimensional line, a circle and then study how the properties will change. Are there any other questions? Yeah, going more into this will be out of overview of this thing. I don't see any other questions.
No, I think this is it.
Yeah, so this is it.
So, So yeah, it's time
Yes.
to thank Rishabh, Preetham, and Argo, who I think who has already gone for some next experimental task.
Yeah.
Okay. So thank you, Rishabh and Preetham,
Thank-
to take out your time on a Sunday and to give us a fine tour of your lab.
Yeah,
So
our
thank you
pleasure.
very much for the audience. The next session will happen on coming Sunday at Prithvi Theatre at the usual time of 11 o'clock. So thank you. Thank you for joining.
Thank you, Ullas, for knowing us. चाय वाय पिलाओ चलो